In this video, I will review some basic techniques for computing the limit of a function at a point. It will be a very quick summary. You won't become an expert just from watching it. You would need to do further practice yourself. But at least, if any of the things I mention is foreign, it suggests what to work on. First thing to try with a new limit, check whether the function is defined and continuous at the point. If it is, evaluate and you're done. Here is an example. I want to compute this limit. The function is continuous in its domain. 2 is in the domain. So to compute the limit, I evaluate at x equals 2. And that's all. If the function is not continuous, what do? Try doing some algebraic manipulations to convert the function into a continuous one. The manipulations only need to be valid near the point, but not at the point. So for example, it is okay to multiply and divide by something that is 0 at the point, as long as it is not 0 near the point. For example, a common and useful manipulation is factoring. I want to compute this limit. The function is continuous on its domain, but 2 is not in the domain. If I try to evaluate at 2, I get 0 divided by 0. This tells me that I can factor x minus 2 in both the numerator and denominator. Now I can divide both by x minus 2. The new function is continuous at 2. So I simply evaluate at x equals 2. And that's it. Here is a different type of algebraic manipulation. I want to compute this limit. This function is not defined at 0. If I try to evaluate at x equals 0, I get 0 divided by 0. The numerator is giving me trouble because of the square root. I would like to get rid of it, and I can do that if I multiply the numerator and the denominator by the conjugate. Now in the numerator I have difference times sum, which is the difference of squares, and that will get rid of the square root at the top. I can now simplify the numerator. Then I divide both the numerator and denominator by x. And finally, the new function is defined at continuous when x equals 0. To calculate the limit, I simply evaluate at x equals 0. And that's all. The third method is to try to transform the limit into a different one that you have already solved. I will illustrate what this means with an example. It is a very specific one, but it will clarify what I mean. I want to compute the limit as x approaches 0 of sine of 2x over x. This limit reminds me of another one I know. I know that the limit as x approaches 0 of sine of x over x is 1. It's almost the same, but I have 2x as the argument of sine. Well, what about the limit as x approaches 0 of sine of 2x over 2x? If I think of 2x as the new variable, as x approaches 0, so does 2x, then this limit is the same as the previous one. So the limit is also 1. Now, back to the original problem. Can I transform this limit into the one whose value I know? Yes, I can. Just multiply it and divide by 2. And now I notice here inside the function whose limit is 1. So the total limit is 2 times 1, or simply 2. The same idea can be made more interesting. I want to compute the limit as x approaches 0 of sine of 2x over sine of 3x. With the same argument as in the previous example, I can conclude that the limit as x approaches 0 of sine of ax over ax is 1 for any non-zero constant a. So in this limit, it would be quite convenient if I have 2x divided sine of 2x, and I had 3x divided sine of 3x. I can get those there if I multiply and divide by a bunch of terms. Look what happens now. The limit of this piece is 1. The limit of this piece is also 1. And the limit of this piece is also 1. So the full limit becomes 2/3. Here is one final example. Naturally, the most interesting limits may combine multiple methods. For example, I want to compute the limit as x approaches 0 of 1 minus cosine of x over x squared. I cannot evaluate at x equals 0. I do not see how to simplify this function just yet. It has a cosine, but the only trig limit I know has sine instead. The trick is to multiply and divide by sort of the conjugate, by 1 plus cosine of x. How does this help? Well, the numerator now becomes 1 minus cosine squared, which is the same as sine squared. And there it is. I found a sine to group with the x. Here I have the product of two functions. The first one I know has limit 1. And the second one is well defined and continuous at 0. So to compute the limit, I simply evaluate. And that is all. So those are the main basic methods. Check if the function is continuous, manipulate it algebraically, and reduce to a problem we have already solved. Of course, there are always more methods. For example, the squeeze theorem is very useful for certain limits. And then there are some advanced methods, but they require knowing other concepts. There is L'Hopital's rule, which requires derivatives, and even better, we can use Taylor series, which is probably the most powerful method for limits, but it requires knowing about power series.